lecturer today, Patrick Johnson. He's an assistant professor at the Department of Architecture at the National University of Singapore. He's also the director of the Design Automation Laboratory. He received his PhD from the Hong Kong Polytechnic University. He has his master's from Westminster University and his AA diploma from the Architecture Association. Along with what Patrick shares with you today, he conducts research on computational methods for architecture and urban design that combine design exploration algorithms with performance analysis and simulations. So we also had the pleasure of working with Patrick for the summer. He was here for about 8 months. So he'll also be here by the time you guys have your critiques. So that's actually something perhaps you can maybe join the critiques, Patrick, when you're back. But that's up for discussion. So without further ado, I'll let Patrick take the course, or take the lead.
Okay, thank you very much. Thank you for ETH for inviting me to do this lecture. And so hopefully I will get it all covered in 40 minutes. I think that's the allotted time. And then we can have some Q&A afterwards. So, okay, starting with methods and tools. So really this lecture covers some work that we've done at NUS from about October 2014 to now. So it's really quite recent work. And it's still kind of work in progress and stuff that we are developing further. And the work is a mixture of, as you will see from the presentation, the work is a mixture of student projects and tools and kind of software plugins that we've been developing ourselves. So, and basically the whole focus of the work is the methods and tools for urban design. And really what the crux of it is that through the urban design studios, we find more and more that there's not really tools appropriate for the types of projects that they're doing in Asia. So the types of projects tend to be fast and large scale, and the urban design tools tend to be just too cumbersome and too difficult to use when you're doing this kind of fast, iterative design process. So first, I want to start with giving a little bit of context about Asia in terms of the types of projects in urban design that are sometimes tackled. And so I think these projects tend to be quite different in scale and in speed from the types of projects you get in Europe. So this is what maybe is called, might be called accelerated urbanization. So the urban population is in Asia is actually lower than Europe. I mean, usually these talks start with the fact that 50% of the population now lives in urban areas, and that in some ways that's surprising. In some ways it's not. It's surprising that it's not more. Because when you think about it, when you live in Europe, how many people do you know who live in urban areas, and how many do you know who live out on a farm? There's a lot more people who live in urban areas. So in Europe, the urbanized population is more like 70%. And the reason that globally it's only 50% is that in Asia and other third world countries, it's actually lower. So the current urbanization levels, if you look at the graph at the bottom right, or also the image on the top right. So these images were taken from the web, sorry for the low resolution. Usually I don't project them on such an enormous screen, but they look a bit blurred. But I think they still clear enough. So when you look at places like Thailand and Philippines, well, Thailand is still below, it's like 37%, somewhere around that. And then when you look at the top right image, you can see that quite a few places are still much lower in Europe in terms of their urbanization, level of urbanization. But obviously the big difference in Asia is that the speed of urbanization is absolutely massive. So the change over the next 10 or 20 years or 30 years is going to be huge, simply because the existing cities can't accommodate the influx of people who want to move to urban areas. And just as one example of that, you could look at the Delhi-Mumbai Industrial Corridor, which is this, one of the mega projects in India. It's a kind of industrial strip from Mumbai to Delhi, and it's about 1,500 kilometers long. And along this strip, they're going to build infrastructure, an industrial kind of belt, and a series of megacities. So they're planning at the moment 7 new megacities. So these megacities, many of them are really cities that are being created from scratch, out of almost nothing. And their purpose is to, because places like Mumbai and Delhi cannot cope anymore with the number of people who are moving to those cities. Those cities can't just keep growing. So they actually have to build new cities to accommodate the urban growth, the growth in urban population. And those new cities have to be built very, very fast at very large scale. And so these kinds of projects, offices in Singapore, the students that we have in Singapore in the urban design courses, some of them will be working on these kinds of projects because the offices in Singapore do, the urban design offices do work on these projects all around Asia. So one of these new megacities is the Gujarat International Finance Tech City, and that one is projected for about, the site is about 8 square kilometers, and there's not so much information about the number of people. Mainly the information you get is how much it's going to cost, but not very much about the people who are going to live there. But the fact is that whether it is good or bad is not, the issue. The fact is that these things are going to be built. And what we need to try and do is to try and find ways to ensure that these, when they do get built, they're as good as they possibly can be. So the image on the top left is the plan for the city. The image on the bottom right is the current situation. 2 towers are being built, and there's some construction going on. But I think if you come back in 10 years' time, there probably will be a large city there. So this is just a kind of one-off example, and there are the same kind of things happening in China and in all the parts of Asia. So really, this kind of scale and speed requires different kinds of methods and tools from the tools and methods and tools that you would usually use on much smaller projects. And so this is one of the issues that we're trying to deal with. And really, this whole issue it wasn't something that we set out to try and solve in advance. It really sort of emerged as we were working with the students on some different projects. And so the project that I'm going to talk about today is this case study project. I'll come to that a little bit later. I'll first talk about the issue and then I'll come to the case study project. But the case study project is going to be for a project in Singapore, but it's also a very large-scale project and also requires some of these methods and tools. So first, focusing on the issue. So the issue is that the existing planning support systems, which were developed really in the late 80s, and in the 90s they started becoming popular when PCs became cheaper. Planning support systems started being used, and GIS being one of the main ones. But really these tools for urban design they're pretty cumbersome tools. They are mostly, they're nearly always 2D tools, and they don't really support the iterative design process very well at all. They're very sort of focused on data input and output and data analysis, but not really focused on the design process. So when you look at the design process, and this is an image of one of the student groups that were working on this project, what you find is that the reality of the design process is that it's very dynamic, it's collaborative, there are very strong time constraints, everybody has different skills and software tools, and the tools themselves have lots of inbuilt constraints. And this is the situation in a group of students working together on a project, but it's also actually the same situation in practice. Practice is also dealing with these same issues and same kinds of problems. So looking now at the case study. So the case study is based on the project that we did with the International Forum on Urbanism. So earlier this year, in January 2015, the IFOU had its winter school workshop in Singapore. Singapore doesn't have a winter, but it was still called the Winter School. It was for 2 weeks, for a period of about 2 weeks. 180 students came from all over the world and participated in this workshop. So we did have some students from ETH. Is anyone here from ETH who was at the workshop? No. All right. We had a few students from ETH and students from all over the world. So from Japan and China and Hong Kong, Australia, Philippines, from really all parts. And the topic of the Winter School was it was organized by the Jurong Town Council, which is one of the government bodies. And it was to transform this area that's shown in this plan here. It's an area of 5,000 hectares, which is currently in the west of Singapore. It's currently an industrial zone. And currently there's really no residents who live there. It's all industry, and they want to transform this area into what they are thinking about as an industrial city. And the image on the bottom right there shows that their initial ideas about developing this industrial city, including green belts and blue water areas and transport systems, underground goods mover systems, so planning systems where cargo will move underground rather than on top of the streets. So it's a very ambitious and large-scale project. And so as part of their planning for this area for 2050, planning ahead for 2050, they invited the International Forum on Urbanism to focus on this as their winter school project, and to try and get the students to brainstorm ideas about the possible future for this area. So this is really I don't put much text on my slides, but this is the one slide with some text on it. The transformation of the Jurong West area from a monofunctional, segregated and fragmented and highly polluted industrial area into a major catchment for future population growth that integrates cleaned industrial plants with green lungs, attractive housing and vibrant urbanity for 1 million people. So so really when you look at it, it's 5,000 hectares, and they want to house 1 million people there by 2050, and they want to do it in such a way that they are integrated with industry. The idea is to go away from this outdated concept really now that industry has to be at one end of the city and the people live at the other end of the city. Now, the types of industries we have, a lot of the industry is a very clean tech. They don't pollute. They, in terms of noise, ventilation, all the issues that you used to have with industry, a lot of those issues are not there anymore. So now it's actually possible to integrate industry and housing and commercial areas into one city, as it were. So that's where the idea of the industrial city comes from. And so they really were looking at this area and wanted to get ideas about how to approach this. So just to jump straight into the end of this project, because I'm not really going to, this project goes throughout the whole presentation, but really the winter school part of it, which was a 2-week workshop, was just one small part of it. So group 9 was one of there was like 12 groups, I think 12 or 16 groups, I can't remember. But group 9 were the winning, there was a kind of competition at the end and they won the final prize. And so they proposed this, let me see if I move my mouse. So they proposed to take this area of water here at the front. And can you see my mouse moving? Yes?
Yeah.
You can. To take this area of water here and dam it up with 2 dams to turn this into a water catchment area for Singapore. Because one of the problems for Singapore is that they don't have enough fresh water. So this becomes a huge reservoir for water, and then they propose a whole series of ideas for this whole area behind here. And they had about 10 days to develop this project. And so I just grabbed a couple of images from their final presentation. But some of it was at the large urban scale, some of it was more at the neighborhood scale, some of it was more detailed. And it really looked at it's amazing what they produced in 10 days. A group of 10 students who didn't know each other before that, and they all got together and produced a kind of very convincing and interesting project in 10 days. But there was I think one of the things that were lacking from this group and from all the other groups was that there was a general lack of quantified evidence. There was, when you are designing, a small area, a few blocks in a neighborhood, the problem of quantifying things is not so large. So if you're designing an urban project at a small scale, you can really, by eye, you can sort of estimate what the floor area might be and how big it should be, how many people are going to be able to be housed or work in these buildings. But when you're looking at this project of this kind of scale, when you're looking at these 5,000 hectares in one go, there's actually very little intuitive kind of understanding of how many people can be accommodated. So when we are looking at these projects, and we evaluated a whole series of these projects, the question is always, well, the design brief said, it has to be for 1 million people. We have to have a mixture of industry and residential. There are different quotas for industry and how much industry you need, how much residential you need. But really none of the projects in that 10-day period managed to give any idea about whether they achieved that, whether they provided too much, whether they provided too little, and whether, that's the kind of basic level. And going a little bit further forward is also whether there was any analysis of the impacts of different options. So if you've developed 2 or 3 different options, how do you evaluate whether one option is better or not? So this was really the starting point for this whole idea to try and think of better workflows and better methods and tools to be able to analyze, to generate and analyze different options, and to be able to back up your claims with better evidence. So looking at this cycle here, the first stage is really data collection. And for the IFOU's winter school, we did that part quite thoroughly. So we collected a lot of data from before the students arrived at the winter school. We collected a lot of data about the site that we were working on and provided that as a set of GIS databases. Then, can I just ask, out of the students there today, how many do use GIS? Can you put up your hand if you're a GIS user? Yeah, I think it's kind of the same proportion that we had in the winter school. There's always like the 5%. So really these tools are still, even GIS I think is still very little used. So then the next stage then was what we're interested in is data synthesis. Is really about being able to generate models of these projects. Because at these high density, 1 million people in 5,000 hectares is really quite a high dense kind of project. And so when you are at these densities, planning through zoning, planning by coloring in maps doesn't work anymore. You have to be able to generate 3D models to be able to see at different densities how things are interacting and what the spaces feel like, and really to understand what the impacts are. So planning in 2D doesn't work anymore. So really, big part of data synthesis is synthesizing 3D models. Because when you're going to create a model for 5,000 hectares, you're not going to sit there clicking, because you'll be clicking for the rest of the month. You're going to have to use some sort of automated technique to generate these models. And then the third step is data analysis. So once you've generated these models, what kind of analysis can you do? How can you analyze not very complex things, quite simple things? I mean, starting with simple things like what's the floor area of your model, to then gradually more complicated things like what are the densities, how do you represent different heights and densities, travel distances. And so at the end of this presentation, I'll show you an example where we started analyzing some of those things. But really, there are many other things, and we will also look a little bit at the future, other types of things that could be analyzed when trying to work with such large-scale proposals. So step one, data collection. So just quickly to give you some sense of the way that the data was collected for starting this project. So this data was given to all the students in the winter school when they arrived, and it contained the GIS data, but we also converted the GIS data to a series of different CAD formats, so students who didn't know GIS could use those CAD formats. So really kind of three main methods that we used: downloading data, tracing, some tracing had to be done, tracing data, maps, and then some web scraping, which is probably the more advanced kind of part of it. So the downloading data, the government, the Singapore government produces quite a bit of data and publishes it on a website called data.gov.sg. I think a lot of people imagine that in Singapore we have enormous amounts of data all freely available. Actually, that's not the case at all. Most of the data is, like in so many countries, very distributed, not integrated, very difficult to get hold of, and the government agencies are in general very reluctant to give out data. So actually just downloading data is a lot of work, because you have to go to different sources and try and integrate all the different data sets. Tracing data, because the maps that we have no, the government has no vector-based maps of Singapore that they're willing to share. So we are basically using the OpenStreetMap maps, and in those maps there is a lot of errors and mistakes, and so we then need to correct those errors by tracing non-vector-based maps. So this is kind of laborious work, but just so you understand a little bit the process that goes into collecting this type of data. Some of it is time-consuming and laborious, but it's really, without this kind of base data, there's very little else that we can do. The third kind of technique we used was called web scraping, which is basically writing scripts, programming small scripts that go to websites and download specific bits of data. And so this was used for downloading all sorts of data, housing types and business listings and address points and a lot of different data on different websites. A lot of this data is basically in Excel kind of formats or in text-based formats, so it's not geolocated yet. But through the address points, it is possible to geolocate that data. So this is just an example of, on the left is a kind of Excel file, well, it's a text-based file with some data about 1 room, 2 room, 3 room, 4 room, and 5 room flats. And then it's a question of using these postal addresses to then link the data back to geolocated database, so that this data can then be imported into the GIS database. So none of this is particularly new or anything, but it's just the process that we had to go through to actually get a data set that we could start working on. And this then produces a series of maps that are all GIS-based maps, so they all have attributes and data inside them that can be used during the design process. I've just seen that I'm halfway through, and I can see that I'm not halfway through my points here. I'm going to speed up a little bit. So then, the next step is the data synthesis, which is a little bit really the more interesting step. So tools are needed to generate large-scale 3D models. And they need to be large-scale because the site is large. So the generation process will be highly automated, but nevertheless, we don't want to generate the same typology over the whole site. We want to be able to generate different typologies with urban variation. So we did a few experiments with existing tools, and one of the tools that is well known is City Engine. And it's very good for making models for visualizations. But for this large-scale kind of modeling, it's not very flexible. So the level of automation is actually quite limited. You still, every time you're creating the model, you still have to do a lot of manual interaction to control your model. So we developed a different kind of approach, which was really using a tool called SideFX Houdini, which is a parametric modeling tool for the animation industry. It's a tool that can be freely downloaded, so if anybody's interested in using it, you just Google SideFX, and you will see there's a download link, and you can download the tool for free. And it's a kind of advanced parametric modeler that can do very large-scale models, mainly because its background is from the animation industry, so the size of models that it can deal with is much larger than the types of models that Grasshopper or Rhino can deal with. So one of the approaches that we then started to explore is to say, okay, let's say that we've got some kind of parametric model that's shown on the screen here, these three models. These three models are actually all the same model, just with different parameters. So if we want to place this model over the site, we want to actually populate the site with this model, then how can we go about doing this without actually having to create each model individually? And so really what we're trying to achieve is to be able to populate the site with this model so that there's variation throughout the site, and so that we can start getting some sense. We're not really suggesting that these models that we generate are going to be the final models that are going to be built. But really more, it's part of the design process to start trying to generate and understand the distribution of functions and plot ratios and densities throughout the site. So one of the approaches we came up with is to use image-based mapping. So for a model, a parametric model may have a set of parameters. And for each parameter, we create an image map. So the areas of black may be that the parameter is a high value, and areas which are white, the parameter is a low value. So let's say with this top left image here, the black areas are around train stations and underground train stations. So whenever there's an underground train station, the floor area ratio, the plot ratio, is going to be higher. So whenever you place a parametric model on the site, it will automatically generate a higher plot ratio when it's close to the train station. And it gets less when you move away from the train station. The number of floors increases as you go along this central corridor. The percentage of manufacturing and industrial increases towards the south, and the residential increases towards the north. So through these image maps, you're starting to plan different functional distributions, different building heights, different plot ratios. And so once you create your image maps, you then just automatically generate the model, and the model is just generated within 60 seconds approximately to generate one model. So you can easily change those image maps and generate a different model. I'll show you a little bit more detailed version of this in another example a bit later. So we developed some of these modeling techniques, and we took two projects that were developed after the winter school. So during the urban design courses, they took some of the projects from the winter school and developed them further. And one project was this one called Ecotopia, and the second one was called Urban Metabolism. And both projects had come up with a series of kind of rules and distributions and plot ratios, a whole set of data for the proposals of this area. But they'd done it without any of these tools. They'd just done it manually. So we were interested in analyzing their projects using these tools and methods. So we took the two projects and we took some of the students from those projects joined us in the research team, and then they reanalyzed their projects using these automated methods. A lot of the projects actually use these kind of rule-based methods already in the way that they design their projects. Even though they weren't using computers to generate these models, they already had these kind of rules in them which said building heights were going to vary depending on the distance to a road or depending on the distance to a waterfront. So here on the right-hand side is just a graphical representation of some of the rules that the students developed. And so we then took those rules that the students had already developed and put them into the generative process to then generate these models for these urban areas, and to then be able to analyze those models and start actually quantifying quantifying the results that they were proposing. So, and I think you know, I suppose it's quite expected really, was that you know, because the students developed these projects without any computational tools, their original proposals were quite far off the mark. I mean, they either produced way too much density and way too many buildings for 1 million people, or they produced far too little. I mean, it varied very widely. And so when you're doing this kind of project, this can have a huge impact. If something works at one plot ratio, it may not work at all at another plot ratio. So through this process of applying these tools, we were able to actually achieve the targets that were set and be able to give evidence that those targets were actually being achieved. So we could actually generate the models, calculate floor areas, calculate how much industry, how much residential, how much commercial, those kinds of things, so that we could verify that these projects were actually working. So, but at this stage, we were just generating the models. We weren't really doing any kind of form of analysis apart from just calculating floor areas. So the next stage of the project was the data mining stage, was to say, okay, we've figured out a way to generate these large-scale urban models, but how can we analyze them? How can we get some more feedback about performance from these models? So really, when we're thinking about this type of data analysis or data mining, there are two types. One is 2D GIS-based kind of analysis, and the other is 3D analysis using 3D models. So the 2D analysis is obviously more limited in some ways, but actually at this scale, the 3D analysis starts to become very slow. This example on the screen here is some work we did on a different project where we developed some analysis methods to analyze large-scale housing developments from a bunch of performance criteria in 3D, so actually accurately evaluate these models in 3D. But when you're dealing with 5,000 acres, this kind of evaluation is just too detailed and too slow. So the 2D evaluations are actually much more powerful at that scale, but we need to include some information from the 3D model. So really what we're looking at is some kind of workflow where you start with a 2D GIS database. This is the data collection part. From this GIS data that you start with, you generate 3D models using various parametric techniques. And then once you have the 3D model, you have three options that we're kind of interested in exploring. The first one is to take it into game engine environments where you can experience the model in 3D in a more interactive way. The second one is to use GIS again in 2D to analyze the data from the 3D model. And the third one is other types of techniques. So we are mainly focusing, in this lecture, I'm mainly focusing on this middle one, generating the 2D data. So how to go from a 3D model to a 2D data. So the tools we're using are all either open source or free, because I think that's one of the important factors in getting these things to work, is to use tools that are easily available. So QGIS is an open source GIS software, and Houdini is a 3D modeler. Unity 3D and Unreal are free game engines that you can download for free, and then QGIS back again. And in QGIS, the kinds of analysis we are interested in doing are the color maps, basically mapping different values like densities and building heights, buffer analysis, which is mapping, doing a type of analysis where you're calculating distances to certain points. So you maybe want to calculate how many people live within half an hour from a train station. So if you have two different urban options, you might be interested in seeing which option puts people closer to points of transport. And then there are other more advanced ones, network analysis and space syntax, which are really more of a future workflow. So how to go from a 3D model to a 2D GIS system. So GIS systems use shape files as the kind of key way for importing and exporting. And so when we are exporting from a 3D CAD system to a GIS system, we need to export a shape file that includes certain types of data. So the data that can be included is basically extracted from the 3D model. So you have these 3D models, you extract certain data, and this data then goes into the 2D shapefile. So this is just a diagram showing how roughly it works. So you have a parametric model with some parameters. When changing the parameters changes the parametric model. I can just show you a brief snippet of that. So this is the model in Houdini here. And every time, let's say I change the plot ratio, as I change the plot ratio, it goes, the configuration changes. Or if I change the intensity of industrial functions, so if there's no industrial functions, red is the industrial part. So if there's no industrial functions, the industry disappears. If you add industry, it adds different layers of industry. Or if you change the residential intensity, it also changes from no residential to residential, and same for commercial. So these models, sort of, the parametric model automatically reconfigures itself to achieve these parameters. So this gives you a kind of, so this is an example of the constant intensities but different plot ratios, and then another example with a constant plot ratio but different intensities. So just changing these parameters changes the model that you generate. So once you've generated your model, you then extract a set of 2D planes out of your model which represent all the floors in your building. And each floor is then tagged or has some data attached to it which describes the 3D model. So the data that is attached describes the floor areas, how much industrial, how much residential, the different kind of uses that you have. And that's then exported to the GIS system. So in order to start trying to think how this can help design decision support, we're looking at this kind of workflow where you create, for each of your design options, you create some parameter fields. These are the parameters that are input into the parametric model. You generate the models from the parameter fields, and then you analyze the results in the GIS system. So in this image on the right here, you can see we've just selected, we haven't done the whole of the Jurong West area. We've selected one area in the middle where we're going to focus on, and this is targeted for about 500,000 people to be living in this area. And so these are the images at the bottom are basically the parameter fields. These can be, are basically created in Photoshop. You overlay them on the site and you shade in the parameter fields using brush tools. And these parameter fields then generate the model. So here in this example, you can see there's 4 parameters that are being used, the plot ratio and 3 functions, industrial, residential, commercial. So depending on the parameters, the shades of these black and white images, this creates parameters that then influence the generation of the model. So option 1 was an example of some students trying to create one version of this model, and then this version is then, the images generate the 3D model, and the model is then exported to the 2D CAD GIS system on the right here. So this is imported into QGIS. Once inside QGIS, we can then very easily do all this kind of analysis. So we can just take the model now, which has been turned into a 2D model, but includes the data from the 3D model, and we can do various types of analysis. So number 1, top right here shows the density of people, so the color shows the density of people, red being higher. The GFA, this number 2 shows the gross floor area on each plot, and number 3 shows the building heights. And of course, you can analyze any number of sets of parameters that you're interested in. So very quickly, you just pick the parameters you're interested in. You can also calculate other parameters based on existing parameters and start analyzing your site and your design proposal. For this particular option, the total residents that it could accommodate was over 900,000. So actually, this option produced far too much floor space. I mean, the size of the buildings, the densities were just much too big. And then in terms of the distances to the train station, then the percentage of people at a close distance to the train station was quite low. So the aim was to try and create another option which would reduce the number of residents and increase the number of residents which are close to the train station. So modifying the images, changing the images a little bit, it doesn't take, the process can be very iterative. It only takes a few minutes to start changing the images, and generating the new model takes 60 seconds. So very quickly you can generate a new model. You can, from that new model, you can generate a new GIS database, and from the database you can run another set, the same analysis. I mean, actually the analysis just updates automatically when you import the new model. And so you can see the new kind of distributions, and you can generate the data for the new calculations. So in this case, still a bit too high, 650,000 people. The residents that are close to a train station is improving. But of course, this is just 2 iterations of something that could go on for many iterations, gradually tweaking and improving the design. So that really takes us to the stage now. I mean, this stage is sort of where we've come to in the analysis process, and where we say, okay, we're starting to get this workflow working, where students without very advanced skills in programming or in GIS can very quickly start iterating and producing urban proposals at very large scale, and being able to evaluate them and analyze them and get data out of them. So the game engine part is also something we're working on, but I don't really have very much time to go into it. But basically, from the same 3D model, we can export an OBJ file that can be imported into one of the game engines, and then you can explore it interactively in a game engine. And there's a lot of possibilities in game engines to do things like make it rain and have wind and noise and experience your urban environment in a very different kind of way. So the 2 game engines we've been experimenting with is Unity 3D and Unreal, and both of them have free versions that are, can be downloaded and used. So I think this is also a kind of interesting area. But for this talk, we're kind of really focusing more on the simulation part. So for the future work aspects of this research, I think really what we'd like to do, at the moment we're doing kind of floor area analysis, some analysis of densities, and we started using this thing we call buffer analysis, where you analyze certain percentages of people and of functions to certain points or areas in the city. But there are many different types of analysis that could also be very useful in the design process. And so 3 things we're focusing on now are isochrone analysis, space syntax analysis, and walkability analysis. And these are all kinds of analysis that make a lot of sense at this scale, at these large scales. All these types of analyses are types of network analysis, and they all require a well-defined network of roads, transport links, and other pathways. So this is, at the moment, the challenge is how to, when we're generating these 3D models, we also need to generate the networks. At the moment, we're just generating the building forms, but not the networks. Once we've got these networks sorted out, we will then be able to do these types of analysis. So isochrone analysis analyzes from a particular point in the city, how far can you get in 10 minutes? So let's say there's a point somewhere here in the center of this blob, and it works out whether you're taking the bus or the train or whatever. If I've got 10 minutes or 20 minutes, how far can I travel? So when you're planning transport systems and other kinds of infrastructure, this becomes a kind of very useful tool. Space syntax, I think perhaps you've already, or you probably will get some other lectures on space syntax, I think, because it's a technique that's used quite a lot. But again, we would like to integrate this into the workflow so that using space syntax analysis is much easier and less error prone. And then walkability analysis is another big issue, I think, in all cities and also in Singapore. Being able to encourage more walkability and reduce dependency on cars is a huge issue. So again, we need more tools and more methods to do walkability analysis. So conclusions, I'm almost in time. Really, so it's a kind of, I can't give you really one set of, one answer. There's a kind of ecosystem of tools. We're trying to develop an ecosystem of tools that are kind of either open source or free, and to try and develop workflows that connect those tools in ways that are easy for students and urban designers to use, so that when dealing with these large-scale projects, quantitative feedback can be included in the design process. And so, if anybody's interested in any of the examples or tools that we've created, I'm quite happy to share them with you. And in the near future, we'll be putting together a website that kind of catalogs all these tools. And then in the further future, this slide that's on there at the moment, in the not so near future, let's say, the idea is to develop a platform that actually supports this kind of process in a way that's much more intuitive and much more integrated. And the aim of all this, coming back to this bizarre image in India, and the aim of all this is really to try and give people tools so that they can do a better job. I think at the moment these things are very difficult, and because they're difficult, people don't do them. Even people, you know, working on huge projects with a lot of money, these kinds of analysis processes are often only done at the end and not part of the iterative design process with bad consequences. So the aim of all this is to try and improve the urban environments that are going to be created in the future. Just a quick mention of the collaborators. Dr. Rudy Stoofs at NUS is my colleague, and we've been working closely together on all these things. And other staff that have been involved is Dr. Zhang Ye and Dr. Zhang Ji. And the research assistants on the main parts of this project were Lin Xiong and Elvira Tan. And thank you very much. 2 or 3 questions? I can't hear the question. That's better.
So we So,
Can you hear us, Patrick?
Yeah, I can hear you. I can't see you, but that's all right.
okay.
Where are you?
Just here. Hello.
There, okay.
Okay,
Hi.
just thank you very much for your presentation. Just one short question. So, to me, it looks like this is a kind of master planning, yeah? So, my question would be, what is your stance on master planning? Do you still think it's an adequate answer to the problems of 21st century city, this kind of conception?
Well, I think that's, yeah, I mean, it's a more emergent kind of urbanism is, sorry, can you hear me or not? Yeah. There's some construction going on, so hopefully you don't hear the drill too badly. A more emergent, bottom-up sort of urbanism is, of course, very desirable. The problem is that it's just the issue of speed and scale. So the types of projects that are being developed in Asia just tend to be very fast and so large scale that inevitably they end up being done in a top-down way. Now, whether that is good or not, I'm not really sure. I think it's not good in the sense that a bottom-up urbanism would definitely be a lot more interesting and more varied and produce a better kind of environment. But the problem is that the people who are now living in the countryside and who want to move into the urban areas are not going to wait. So they're going to go one way or another. And so either they end up on the outskirts of some huge existing cities in the slums, or they move into these new top-down cities. And so if these top-down cities are going to happen, then I think it's, important to try and make them happen in a way that's as good as possible.
I'm sorry, can I just give a short comment and then I will stop?
Yeah.
So I think, especially in Asia, if you look cities like Jakarta or these kind of cities which are growing at the rate of 500,000 or 1 million people per year, these should be the cities that can actually show us that the idea of master planning is not adequate for them, because you cannot plan as fast as these people are coming. So, yeah. Okay, thank you.
Well, I think that's, I think it depends a little bit also in the context. I suppose for the Singapore project that I've been talking about here, they plan very much top down, and it generally works the way that it's planned. It's a very controlled environment. In places like India and Indonesia and places, the mixture between emergent urbanism and top-down planning is much more complex, and sometimes it's ugly and sometimes it's less ugly, but yeah, I think it's a very complex kind of situation. Any other questions?
Yes.
Hello. I just wanted to ask, I mean, a lot of your parameters are all quantitative, and right now there's a growing trend of kind of crowdsourced development and crowdsourced map making, and I wonder if there's any potential to be using experiences or information or data collection from the common population, from people moving in, to help develop what's happening here.
I heard something about, I couldn't quite hear very well. I think the question was about the use of crowdsourcing to inform these kind of methods?
Yeah.
Is that right?
That's correct.
I think definitely, I think in the terms of the data collection part of the process, crowdsourcing can be very useful. The one thing that we find, though, with some of these projects, again, which is sort of, I guess, different from Europe, is that so, like, for example, the project in Singapore that we're looking at in the Jurong West area, the buildings and environment that is there currently is going to be almost completely erased. So none of the data that we collect on the existing situation, apart from environmental data, but data about people and about the businesses that are there and the buildings that are there, that is all going to be scraped clean. And so that data is not going to be particularly useful. But I think the crowdsourcing can be extremely useful in collecting more general data to better understand how cities work, how different cultures interact, how everything kind of integrates.
Does anybody else have a question? If not, I have a question for you, Patrick. And can you speak a little bit about smart cities and how that, I mean, kind of, what specific data would help improve your scenarios, not just in Singapore, but in other, in India, for example?
Yeah, I think that's, you know, since we're just really starting to develop these workflows, we've just been looking at the most obvious things. Very obvious things like, you know, how far you are from the train station or something like that. And those basic things, I think, you know, are very universal, apply everywhere. But I think once you start looking at specific cities, there are certainly cultural, environmental, I mean, even the distance to a train station in Singapore where it's hot is you walk a lot shorter distances than you do in Zurich. So I think immediately cultural, environmental, and local kind of issues come into it. And I think the more you start looking locally, the more you start developing methods of analysis that are specific to the local context.
I think that's it. Does anybody have any final questions? Otherwise, would like to thank you for your time and have a good evening.
Thank you very much, and I hope it's all the sound was all right. You could hear everything all right.
Yes, it was just fine on our
Okay.
end. Yeah.
All right.
Great. Thanks, Patrick.
Thanks.
Okay.
Bye.